Okay, so we are going to look at some ideas about fluid dynamics. And when we think about fluid flow or fluid dynamics, we think of two ideas. We want to pay attention to a couple of things. The first, which is covered in a different video, talks about the continuity relationship, the continuity principle or equation. And that tells us that as fluids move from one area to another, the bulk flow rate, so the amount of fluid flowing per volume, the bulk flow rate has to remain the same. You can imagine, otherwise you're going to get some backing up and some gapping in the fluid flow. The other principle that we think about with fluid flow is that energy also has to be conserved. So the conservation of energy principle remains for the flow of fluids. And we think about that conservation in terms of pressure and how pressure affects fluid flow and how pressure changes from one area to another in order for conservation of energy to remain the same. And this principle, this equation that is relating our conservation of energy idea is named after Daniel Bernoulli, who studied fluids. And so this is known as the Bernoulli equation, Bernoulli principle. All right, we're going to talk about it both mathematically and conceptually as we typically do. So it tells us that as we look at fluid flow in a streamline, so we're going to make an assumption that this is this nice, even flow. We're looking at what we call laminar flow, so a streamlined flow, not turbulent flow that causes some disruptions in our system. As we're looking at a moving fluid, if conservation of energy is to be maintained, we need to consider potential energy, kinetic energy, and then, of course, the work done on the system. And that's all done in relationship to pressure with fluids. So it tells us that in one area, at one time point, remember we think about conservation of energy as an initial and final, but we also think about it as at one time point at something and at another time point at something. And when we talk about fluid flow, sometimes that relates to where the fluid is in the system. That the pressure at time point 1 plus indication of the kinetic energy of the fluid, which is given by 1/2 the density of the fluid is going to impact its flow times the speed squared, and the potential energy of that fluid, which is going to be related to the density times g times the height, the vertical location of that fluid. That's not an initial, it's a 1. We're doing 1s and 2s. And that has to equal that same state in any other situation. So at another time point in that fluid's flow, we have those same contributions. Now, this, again, the pressure and the fluid at a given time or location, times plus 1/2 the density times the speed squared at that location or time, times plus the density times g times its vertical position at that point in time. And another way to examine this is that the pressure in a fluid plus these contributions to the pressure in energy form, or how we can think of them when they look like that energy relationship, is constant. And this really is the idea of conservation of energy for a fluid, just like it was conservation of energy when we talked about an object moving. All right, so how do we apply this? Let's talk first conceptually. If we know that this has to the pressure essentially has to maintain the same, these contributions to the pressure. If I blow on the top of this sheet of paper, what are we going to observe? We see that the paper lifts up. If I blow on the top of the paper, we see that the paper lifts up. Try that at home. Why might that be? Okay, well, this contribution goes away. We're at the same height whether the paper is sitting there stationary or the airflow, the fluid is, of course, the air that is in front of the paper, is the same. So that one goes away. So it tells us that if I increase the speed of the air by blowing over the paper, now the fluid above the paper, the speed has increased. In order for this to remain constant, the pressure has to go down. So if this contribution goes up, this contribution goes down. And so the pressure drops in the air above the paper. Well, now the air below the paper is at a higher pressure than the air above the paper, and we get a net force in the positive direction, upward, lifting the paper up. So that's a conceptual idea of Bernoulli's principles, and there's lots of really good uses of that. Airplanes operate on this idea, for example.